I wanted to let you know that these are probably the two most difficult epidemiological statistics that you will learn in this class. So I'll try and be succinct and to the point, and to make your learning as easy as possible. I also want to let you know that there are problems that I think it's important and necessary that you complete that will go with this chapter. And so you want to focus on the direct and indirect method of standardized mortality rates, or as they're known, SMR. Sometimes you'll see the word adjusted, and they are adjusted, and I'm going to tell you how we're going to adjust them. The direct method, we adjust the data in one way, and the indirect method, we adjust it in a different way. So I'll give you some clear criteria as to when you would use one versus another. Okay. Now, this definition, notice it always, every definition we have has the word ratio in it. And this is a distribution. We learned that epidemiology is a study of the distribution of determinants. Well, this is an area where we believe there is a problem with the distribution of data that we have gotten from a special or specific population. So, if I was going to say it again, SMR has to do with a distribution problem in the data. And SMR is a way to correct for that distribution problem. And SMR direct uses age-specific, it occurs when the age-specific data are peculiar, and I'll show you examples where the age-specific death rate data seem to be peculiar, and how we're going to adjust it is against a particular standard, and that particular standard is the U.S. population, and I'll explain why we use that in a minute as opposed to some other standard. And I think it'll become hopefully intuitively clear to you why you would do it, and then why you would make the adjustment. So just sort of follow along and try and absorb it and take in as much as you can the first time, and then you may have to go back and play it again so you're more confident in the things that I've said. Okay, so when we're looking at SMR for the subpopulation or a preferred population, we're going to compare it to a standard population. So let's say in this case we're going to look at Honolulu, Hawaii in relationship, and we are, and in Honolulu County, and we're going to look at that in relationship to the U.S. population, because we want to know a couple of things. First off, is the data skewed? Is Honolulu data representative of the standard population or the U.S. population distribution? And usually, when we make the assumption about the distribution, the two are not the same, and they can be very different, which causes the SMR or accrued death rate to be quite different than what we think it really is. The next thing that you have to, we're doing a distribution method, but in order to do a direct method, you must have age-specific death data for the subpopulation or Honolulu, Hawaii, in this particular case. So if you don't have age-specific death data for the subpopulation, there's no way that you can do the direct method. And this is what separates the direct method from the indirect method. Okay? So somebody says, why do you use the standard population of the United States? Because it's the best estimate of the true distribution of the population, because it's taking into account every city, every county, every state in the nation. And so the data that are collected for an age specific group are going to be the most representative of the US population, where if you take one city, that data may not be representative at all. Now let me see if I can give you an example. If I was going to ask you whether the Purdue University students were representative of, or the city of Purdue University students was representative of the U.S. population, you'd answer no. Why? Because we have more young people. And so this is a factor that we're trying to take into account and we're trying to adjust for. So I want to emphasize again that the direct method cannot be used without age-specific death data for the subpopulation. You must have mortality data for each age group, and I'll point to it on the graphics as we go along. So I want to say this again in a different way. The true representation for an age group is the U.S. population. If I examine a particular city, that city may not represent the true distribution of the age-specific death rate for any particular age group. Okay, so the U.S. population distribution is the best guess of a city, state, or region population distribution. I hope that makes sense to you. So you have to have age-specific death rate in order to calculate a direct method, and you're trying to check to see whether the data of the subpopulation is really representative of the total population, or whether it's skewed, or what we would say skewed or biased in some particular way, fashion, or form. Okay, so what we've said thus far about SMR Direct or SMR, it's a technique to remove as far as possible the effects of differences in age or other demographic variables when comparing populations. Now I want to make the point that age is the most commonly adjusted variable. But at the same time, I'd like you to know that we could adjust not only for age, we could adjust for socioeconomic status, we could adjust for race, we could adjust for any number of things as a test to see whether the subpopulation of interest that we're studying mirrors that of the U.S. population. All right? So, and we know that the SMR method, and the SMR direct method, by the way, is the gold standard. It's the best you can do, and that's why we talk about the SMR direct method first. So this is just to catch you up on the couple of points I've already made, and you've been following along in your book, so you can see them on the slides as well. Okay, now confounding. I don't want to get too far afield with confounding because confounding is a complicated idea, but I do want to introduce you to the notion of confounding because you're going to hear it in any time you deal with data. If you're dealing with data for your dissertation or what, confounding and bias or error are terms that are going to come up, because what we're after is we're trying to come up with a valid or a true score. Okay, and so confounding, as we're seeing here, just means two variables mixed together that we can't separate the effects. That's all it means. Okay, no more complicated than that. So we want to identify what is really the best estimate or the most accurate score that we can obtain in looking at a subpopulation. Now, there are a couple of, I just want to mention this, and you can spend more time going through this at your leisure, that you can differentiate between a moderator variable or a confounding variable. Well, confounding variables come in two forms. They come in mediating variables and moderating variables. All I want to do is make you aware of those. If you're doing a study, you can go back and address those particular terms and find out what it means and find out how you test for them statistically, etc. What I'm trying to teach you right now is that we're trying to reduce confounding variables by using SMR, standardized mortality rate, or adjusted standardized mortality rate direct. Okay, that's the point I'm trying to teach. I'm not trying to teach you a comprehensive course in all matters related to conducting studies. Okay, so why use standardized mortality rates? Okay, we've talked about this already, but I want you to see it in writing, and I want to emphasize it again. We want to offset the effects of skewness or bias. And we talked about skewness could come in the form if we were examining a college population or a senior population. If we went down to St. Petersburg, Florida, we would find out that the majority of people there are older and they do not represent the nation, nor does a community of college students represent the nation on anything that has to do with mortality. So we can't assume that the college population is representative of the nation. Okay, and the best standard that we can use is a U.S. population as in pertaining to some demographic variable, age, for example, that would be a good representation of the actual distribution for that age-specific population. Now, we can use this method for a U.S. population or a world population. And I'm saying it again in another way. I'm trying to say this again in as many ways as I can. The gold standard, as we mentioned, is the U.S. population or the world population. And the gold standard population is the gold standard because it represents the most accurate data or the best estimate of the true population distribution. So that's why we use the world population. I'm hoping that's making sense to you and you're getting an idea about it. So I want to go back and cover, when do I use a direct method? When I have age-specific death data for the subpopulation of interest that I'm going to study. And if I'm going to study Honolulu, Hawaii and Honolulu County, or if I'm going to study a college population, I want to know whether that data is representative and compares to the U.S. population. Otherwise, I'm going to get a result that is skewed and incorrect or biased. Okay, so I would make assumptions about death rates that would be false, and they would not correspond in any reasonable way to what we would expect uh, in regards to the U.S. or the world population as a whole. Okay, so one of the things I mentioned, we have to have age-specific death rates for the subpopulation of interest, and then we have to have skewness, and we will test for skewness. Okay, okay, I've said this, right? Best indication of how a subpopulation compares to the total population. You've heard me say that time and again already. And so we're going to find the total standardized population of the reference group. Always look for the summary value in the denominator of the SMR. And I'm going to go through these steps. And these steps probably won't make a lot of sense to you until I get to a specific example. So we have to have the age-specific death rate for the subpopulation, but it will be adjusted by population scores or distributions, and you'll see that, and I'll point to it and I'll show it to you. So don't get too nervous if you don't get it from just reading these steps. Okay, and we'll deal with the number of deaths in a particular age group and the total population in an age group, and I'll show you how this formula applies and what you do with it. But I just want you to remember the two conditions under which we use the direct method. And you ought to be able to say, what are those two criteria, and be able to list them at this point. And I'll cover it toward the end again, so if you don't understand it yet, or you don't have them written down and you don't have them memorized, you can commit them to memory. Okay, now we have to do some additional math. We have to find the expected death rates for the reference population or the subpopulation of interest, and this is how we do it. And then we will calculate the direct SMR. Now, the K always, in this particular instance, is 100,000. So if you're using the U.S. population to standardize, it's a population statistic, then you're going to use 100,000. Okay, are you with me so far? And you can go back and look at these steps, and I think they will make more sense to you as we focus on a particular problem. So I know I haven't kept you up to date as much in showing you this information on the slides, because I wanted you to listen to me rather than to focus overly on the slides. Okay, SMR direct example. Now, I'm going to read this to you, not because I don't think you can read, but there's some information that's very important that you recognize in this problem. Most of it is delineated in red. It is delineated in red. It says in 1980, and it could be 2000, it could be 2010. There were 228 deaths from lung cancer in the resident population of Honolulu City and County in Hawaii. The population in the mid-80s was 762,565 individuals, giving a crude death rate of 29 per 100,000 population. So how did we get that? We simply divided 228 by the total population to come up with a crude death rate of 29.9 per 100,000 population. In 1980, the crude death rate for the U.S. for lung cancer was 47.9 per 100 population, and that's a given, and I can show you how we can get that. And in order to control for the age effects of these crude rates, age-adjusted rates can be computed by the direct or the indirect method. Okay. Um, I'd like to show you now where we got the the crude death rate. We took let me see, I'm trying to get my arrow to function, and it's a little smaller than normal. We got the crude death rate right from this table. It's 228 divided by this amount gives us times 100,000 gives us 29.9 per 100,000 population. You already know how to handle this. Now, notice that we have lung cancer death rates per age group. Okay? That's the first important necessary step in order to calculating a direct standardized method, a standardized mortality rate. If we don't have lung cancer per age group, specific age group deaths, then we can't do a direct method. All right? This is the standard population. This is the U.S. population of 1980. And you can see we have the distribution of the deaths per age group. And we have the total population at that time. Notice how much our country has grown by looking at these values. Okay, now, so far this should make sense to you. And we're going to have this information. Obviously, I'll talk about the zero because you'll see how we're going to come up with the expected rate in just a moment. Okay, so I want you to remember the 228. I want you to remember the 29 per 100,000 population for the subgroup, which is Honolulu County, and I want you to remember the 47.9 per 100,000 population for the U.S. And in this particular case, that was a given. But notice that the death rates for lung cancer in Honolulu are 29.9 versus what they are for the U.S. population, which is 47.9. This would suggest, if you just looked at it and you didn't adjust the data, that the lung cancer deaths are substantially lower, right, 29.9, than they are in the U.S. So therefore, you might draw the conclusion rather quickly, if I want to avoid lung cancer, if I don't want to be subjected to lung cancer, where should I live? I ought to live in Honolulu City and County in Hawaii. Now, this might be a false conclusion, and it may not be, okay? But we'll talk about that in just a minute. So, now, we're going to talk, let me get to the next slide here for you, and we're going to see whether we can't come up with some values for you, how this table is really completed. Now, I'm going to show you a problem, but I don't want to start with it. How we got this particular score is that we divided 6 by this value to come up with this. So we took the number of lung cancer, specific lung cancer deaths for an age group, 25.4, and we divided it by the total population to come up with a death rate of this value. Okay? So we'll just take these one at a time. The process is the same. Okay, and here's our answer. And we're going to do it for this one. And here's our answer. All right, and then we have another one, and I don't, in this particular case, I don't provide the answer, but you can do the multiplication and come up with an answer. Okay, so that's the first step that we're going to do, and you notice where the subpopulation is. It's on the left side of the table. And you notice where the standard population is in the direct method. It's on the right side of the table. And you have to keep this in mind because with the direct method, they switch. The U.S. population moves over here, and then the subpopulation moves to the right. Okay, so I don't want to confuse you. I want to stay systematic. I want to keep this as simple as possible because people have all kinds of troubles with these particular problems. Okay, so hopefully you're clear that we have to have two things. One, we have to have age-specific death rates for the subpopulation, and we have to have skewness, and I'll tell you how we're going to test for skewness in a minute. We haven't done that, but we're making some adjustments, and we're going to see what those adjustments do, and then we'll test for skewness. And you might do it actually just the opposite way, but it's easier for instruction purposes to introduce the method in this particular fashion. Okay, next. You notice that in the first one, 0 divided by the population is 0, and that's why we have a dashed line here. Now, these are all the values that I showed you previously, all right? Now, the next thing we need to do is we need to come up with the expected rate. Well, we don't have anything here because the next step is going to be multiplication. We would take whatever this value is and multiply it by this to come up with the expected death rate. Now just watch carefully as I do this and show it to you. Okay, so we're going to multiply that value, okay, of the 0.000257 times the standard population, and there's the expected number of deaths for the age group 25 through 44. So the age expected or adjusted death rate is 1,612. Now we're going to do this in each and every case. So just watch how we're going to do it. We're showing what we're doing. We're multiplying the two numbers together. We come up with a value. We're going to do that again, and we're going to come up with a value. And you can go back and do this to confirm it. And we come up with a value, and ultimately we come up with the total. Now here's the U.S. standard population, right? That value hasn't changed. It's been consistent from the first chart to this one. And in order to come up with an age-adjusted death rate, we divide the expected deaths, and there they are right there, summed for you by the total population times a constant of 100,000. So when we look at this, the age adjusted, the SMR, the standardized, this is the standardization process, the standardized mortality age adjusted rate is 40.3 deaths per 100,000 individuals. Okay, so we've done our adjustment. Now, what does it mean? Let's see whether we're going to get back to that. But before I do, and I know that we will get back to it, I want to show you something that often is problematic for the beginner in calculating an SMR direct with this kind of data. Sometimes, now I'm going to go back a slide because I'm going to focus, let's see, I think I'm going to focus right here on this particular. I'm going to focus on the 25 to 44 age group, and I want to show you something. So, because what we always get is some fractionated number. And if you're not getting a fractionated number, you've got a problem, and I want to explain that to you and show it to you. So, if you look at our example here, notice this is death rates per 10 to the 5 power. And if you had something that was like that, and it would come out 2.57, you're going to do the same division, and it happens to be this amount, and then you're going to multiply that amount by this. You're going to come out with a value that is going to lead you to more expected deaths than the size of the total population, which we said previously was 226 million. So if you don't fractionate this number, your expected deaths are going to be greater than the number of people in the standard population. You know immediately if you come up with a value like that, it's incorrect. It's wrong. So you have to have a fraction here, and I'll explain how to do that. That's where I'm leading now. So what we did to come up with a fraction is we took this particular number, 2.57, we divided it by 10 to the 5th power, and we're showing you that. Here's the division process, and here we come up with a fractionated value, which we would multiply with the standard population for that particular age group to come up with this value. Okay? So I want to read to you. So don't. I know people say, "Well, I can read for myself." Well, that may be the case, but I want to emphasize certain points. If you see a death rate that's 2.57, and it says the death rate is 10 to the nth power, which this could be 4, it could be 3, it could be anything else. Right above it, as I've shown you here in this illustration, it indicates in this example that you would divide by the 10 to the nth, okay, or you would make it into a fraction. In this instance, we did. And if you just simply multiply 2.57 by the population for that age-specific subgroup, your expected deaths would be 61 million. Well, if you can imagine doing that for each of the other age-specific death rates, then you're going to have, and you're going to add the expected deaths, they're going to come out to be far greater than the U.S. Population. Ultimately, then, your total expected deaths will exceed the size of the U.S. population, which is ridiculous. It couldn't happen that way, which would not make sense, and you would know immediately that your answer is incorrect. So you've got to look up here, is what I'm telling you. And if it says it's to the 10th and it's fractionated like this, you don't need to worry about it. If it's reported like this, you need to divide by 1,000 to make certain it is a fraction. Otherwise, you're going to come up with something problematic like what I've explained in the note. Okay? Next. So, we're going to test for skewness. And I want to go back to you to show you, first off, where this information comes from and how we came up with the particular percentages. So just bear with me. I'm going to go back. We're going to focus on the subpopulation, and we're going to look at the specific population for each age-specific group. Okay? Now I'm going to go to the math that we used and what we divided in order to come up with the percentages to begin to examine skewness. Remember, I said that was one of the two important factors. Okay, so all we did is we took, if you look now, let me go back one more time so you see this. If you look at this value, you're going to be dividing each one of these values by the total. Okay, so we know how many people, what's the percentage of people 24 and under? What's the percentage of the people 25 to 44? What's the percentage of the people 45 to 64? Are you with me? So let's go back and look. Now you can see under 24 and under, we have done the division, and this is the distribution or the percentage that we come up with. It's still having to do with distribution. All of our calculations have to do with distribution, and this tells you how many we have in each age-specific group relative one to the other. Okay, so that's how we come up with the populations, with the subpopulation percentages. Now we've done the first step, and we use the total of population for Honolulu County. Okay, and so we've got the first step in examining skewness. Now what we're going to do is we have also done it for the United States. And let me show you how we would do that. It's the same process, but let me show you how we would do that for the population of the United States. We would take each one of these and divide by the total population, and it's going to produce a percentage. So population divided by this, population divided by this, population divided by this, population divided by this. Are you with me? So we're just going to replicate it, but we're going to do it for the U.S. population because we want to know the degree of skewedness. Okay, so that's where I got all these values, and you can go back and check them. So what we've got Honolulu County, we got the United States, we've got a percentage for each age-specific group, and we notice that there are more younger people in the 24 and under group by plus 2.4. Okay, now we notice for the 25 to 44 group that we have more younger people in that group by 2.28. And then when we look at these numbers, this value is greater, so we have more older people, fewer older people, I'll get it right yet, fewer older people in the 45 to 64 age group, and again in the 65 to 84 and 88 plus. I may have said this incorrectly, but you know I meant 45 to 64. So, a couple of points here. What do you notice? Well, if you notice here, we have more younger people and we have fewer older people. So this population really doesn't mirror that of the U.S. population. It is skewed. The distribution is different. If it wasn't different, these would all be zeros. There'd be no difference between any of these scores, and they'd all be zeros. Okay? And people ask about, well, when do I do a standardized mortality rate in reference to skewness? Well, I'd probably do it anyway, just because I'm more compulsive and I want to know whether there's anything that's going to change the crude death rate, because that's what we're focusing on, and we're adjusting that crude death rate by the population distribution. But generally, if it's zero all the way through, you would not do it. You would not do in age-adjusted death rate. So you wouldn't do an SMR direct in this particular instance. But in this case, we're definitely going to do it. The population is definitely skewed, and I want to talk to you about that. Okay, so if we begin to add age groups, I added these 24, less than 24, and 44, so we added these two values. Then I took the ones that were in the case where they were younger, and I added these two together, and I want to show them to you now in this table. So this table says again that we have something important going on. We have 5.2% that are younger than the U.S. population, and we have 5.4% that are fewer older people. So if you say it again, we have the difference is in youth. Honolulu is obviously a much younger group of people than that represented by the U.S. population. Now let me see whether I can say this to you again, and I'm going to read to you down here because we're going to disregard the sign here. So we're going to disregard the plus, and we're going to disregard the minus, and you're going to see very quickly that there is a 10.6% total difference when you disregard the sign. So we have more younger people in Honolulu than in the U.S., and that's what I was trying to get across. And hopefully I've stated that well and you understand that. Okay, let's move to the next step. Well, our original conclusion, if you go back to the original problem, when we just calculated the crude death rate for Honolulu, we had 29.9 deaths per 100,000. That was given in the problem. And then we looked at the U.S. population, and we had 47.9 deaths per 100,000. Well, our reaction would have been, well, geez, if you're talking about lung cancer deaths and you want to avoid them, you ought to move to Honolulu immediately, and especially you would come to this conclusion if you had a genetic problem of lung cancer, if lung cancer happened to run in your family. Okay, so now we've done some calculation with the SMR direct. We know that it's skewed. We were able to do some adjusting because we had age-specific death rates. And now what we do and what we've come up with is the adjusted death rate. The SMR direct adjusted death rate is 40.3 deaths per 100,000, right? That's what we went through and calculated. So it's not 47.9 deaths per 100,000 as reported for the U.S., and it's not 29.9. So what we're going to conclude here is the crude death rate, or the SMR, for Honolulu County may be better than the U.S. population, right? Maybe better. 40.3 is better than 47.9. However, it's not 18 points less when you subtract these. It's only 7.6 when you subtract these. So based on the based on the SMR direct, we see that there are fewer lung cancer deaths in Honolulu County than there are nationally, but the number reported of 29.9 deaths per 100,000 is misleading and incorrect. The best estimate of the number of deaths in Honolulu is 40.3 deaths per 100,000. And again, it's still lower than the U.S. population, but it's not as low as we would have advertised and led people to believe. Okay, so hopefully you see the value. We had two criteria we used. We looked at, we had to have age-specific death rates for the subpopulation or the target population or Honolulu County, however you wanted to say it. And then next we had to have skewness. Okay? Now, I want to talk to you about SMR Direct. Now, what happens when you use SMR Indirect? I think I said direct, but you were already ahead of me. SMR Indirect is that you are missing the age-specific rates for the preferred population. They aren't reported, that data isn't collected, so we don't have that age-specific death rate information that I showed you for Honolulu for those 5 or 6 categories of ages. That information is not available. They didn't break it down that way. They didn't want to spend the money on looking at age as a factor in death rates. And we have all kinds of places all over the world where data collection is very expensive, so we don't want to take the time, if you will, to spend money to have to take into account demographic factors that may skew or misrepresent the data. Okay? So again, in the case of Honolulu City or County, when we use an indirect method, we don't have age-specific rates for the preferred population. Now, I want you to begin to think about this table because I talked about it earlier. So the U.S. population, the standard population, was represented on the right. Now, when we go to the indirect method, the U.S. population is going to be represented on the left, and the target population or the subpopulation or Honolulu County is going to be on the right. So the tables are laid out just opposite, and it's important if you're going to be plugging information into the tables that you put the values in the correct you organize it correctly, and that also tells you whether you're doing an indirect or a direct method. Now remember, the gold standard is the direct method. It's the best you can do. It's the best you can get. So when we don't have age-specific death rates for lung cancer for Honolulu, we know that we're going to have age-specific death rates for the United States, and we're going to use those values to make the adjustment. Okay, just bear with me. You'll see it. I'll show it to you. And we're going to have a lot more calculations in this case, and I'll talk to you about that. Now this, if you go back and look at the original problem, in Honolulu there were 228 deaths from the direct method that was initially reported in the problem statement. Okay? Now, I mentioned that we no longer have the age-specific death rates for Honolulu County. That data they just didn't collect. They didn't, they didn't represent it that way. There's no reports. It costs too much. They had other priorities, and if you get into third world countries or socioeconomically deprived countries, they're lucky to have death rates and crude death rates. And that's one of the advantages of having crude information, because you can make some comparisons. Usually they're limited, but you're generally never going to make specific comparisons. You're not going to change a crude method to a specific rate to make comparisons because the data doesn't exist. All right? Now, I want to go through this process again with you, and this should remind you a lot, because we're always looking at observed and expected deaths, and I didn't make that point previously in the direct method, but you should always look at the difference between observed and expected, and that's the same criteria we use for an outbreak, epidemic, and pandemic. Okay, here we go. So I want to show you how we're going to do this. I'm going to not go over these specifically with you. You can read them. I think some people learn better by going by reading, but I think this will make a lot more sense after you go through the process and see it, and then you can go back to this information if you'd like. Okay, so now this is repetitious. When you don't have age-specific death rates for the preferred population of interest, you use SMR indirect. Okay, second, what about skewness? There must be skewness. That doesn't change. So with a direct or indirect method, you got to have skewness, and you figure it the same way. And we say, well, you don't do anything with it if it's about 0. I would say you calculate it anyway to see if there's any adjustment or change in the crude death rate, but leave that up to you. So there's my answer. I've got it printed there, and that would be my recommendation, and I would encourage you to adopt that, but that decision is yours. Now, we do accept the SMR indirect answer. I mean, that would be the standard. That would be, if we're going to do any adjustment, we're going to take the SMR indirect answer as being more valid than a crude rate. Okay? So that's what I'm trying to, the SMR indirect answer is more valid than the crude rate because we've done the adjustment. Okay. Now we're going to use data from the U.S. population to make our adjustments. That's all this says. And I've already made this point before, probably ad nauseum, but to learn it, it's always better to repeat it. And I said that there must be skewness, and there must be skewness both for the direct and indirect population. Now I want to make another point before I get into calculations. You're saying, well, where are these calculations? Now, you cannot compare answers from crude death rates that have been adjusted from the indirect and the direct method because they've been calculated differently. Okay? It's not allowed. We don't do it. Indirect methods are used for within, like you can make a within city comparison for different, for example, for different deaths, and you can do it between cities and whatnot. So you could do it for lung cancer, you could do it lung cancer, pancreatic cancer, heart disease, or anything else for a given geographic location. That's very acceptable for the indirect method. Okay, and for the direct method, you can make country comparisons. Okay, and I've told you about the skewness. All right. So when we use direct method, depends on what data is available, and we know that the age-specific death rate counts are going to be available for the U.S. population just because of the amount of money we spend on data, and I told you that we spend millions on data, and we have multiple data sets that are available, and we call them secondary data sets, as I've talked about before, and you can have access to them. Usually you have to pay for them, though. Indirect method process. It says calculate the age-specific death rate of the standard population. Multiply that death rate from the standard population by their corresponding age-specific population sizes in the study population. Just sort of watch this as we go through. Sum the expected deaths in the study population. Now, by and large, this process is identical. It just depends on where you place the standard population and where you place the data for the subpopulation. Okay? Now, find expected death rates for the based on the US population. Okay? We're going to sum them. And then we're going to go through, and there's different statistics that we can derive from the indirect method that you can't derive from the direct method. You only get one answer and one value from the direct method. You get two forms of data from the indirect method. Okay, so that's another difference. Now here we go. Now notice, when we're looking at the indirect method, you notice that the United States is on the left. Previously it was on the right. Okay? Now, and we have it all divided by age group. Do we not? You can see that we got the same age groups and we didn't change them. Now, this is a heuristic example. It's a teaching example. And usually what you'd have is far smaller age groups. They wouldn't be as big as these. You'd probably maybe have 20 categories versus 5. So I just want to point that out again, that we're doing something for teaching purposes. Okay, let's go through this. So how are we going to come up with this answer? So we've divided 88 by this to come up with this. Okay, there's no 10 to the 5th there, so you're confident of this value. We follow the same process for each one of these age groups, just like you did for the direct method, although the data is switched from the right to the left for the U.S. standard population. Okay, so when we look, after we have that information, we've got it all collected here and we've got it all organized, and here's the U.S. population and here's the lung cancer deaths, so we could do a crude rate. We could divide this number by this number and multiply it by 100,000 and come up with a crude death rate. All right. Now we're going to take these values. We divided these two to come up with all of these, and watch the next step. Okay, it's no different than what you did before for coming up with an expected value, right? So we ask, what are the observed deaths from the problem? Remember, from the problem it was 228 that were specified. Okay, and we've got to come up with the expected deaths, and from this problem it's 285. Then we're going to do a multiplication with, here's where we're doing the adjustment. We're taking into account the lung cancer deaths for the U.S. population. We're taking into account the total population, and after you do the math, and you should do it, we come up with 37.7 deaths per 100,000 individuals. Now, we do have a percentage that we get, and we divide these two numbers. We have the observed and the expected to come up with 80%, and I'll explain that in a minute. Now remember that this value, the 228, is from the direct method initial problem statement, and you can go back real quickly, thumb through your manual, and get that information. Okay, are you with me so far? So our SMR indirect answer is 38.7. That's our crude death rate. That's been adjusted by the U.S. population because we didn't have age-specific information in death rates for lung cancer. Okay. Now, the direct method, we came up with 40.3 deaths per 100,000. In the indirect method, we're coming up with 38.7 deaths per 100,000. Remember, you can't compare the two. You can't compare the answers that we got from one method versus another. The more valid of the two measures is the 40.3. Okay? So if you have a choice of what you can report, and you won't because the data will either be available or not, you'd rather report the 40.3 based on the direct method because that's the best of the two methods. Okay, so but I can't make a mental comparison between the two answers, but it's just not legitimate because they're calculated differently. So it says close but not the same, and remember that they're calculated differently. Okay, how to interpret. Okay, when we get a percentage from the indirect method, 100% is a null hypothesis. This means everything is even, and I'll show you what I mean by that. In the SMR indirect of 80%, it's less than 100% by 20%, right? Less than the standard or what might be expected in deaths. Okay? Now, the next one, if you got an answer that was 110, then it is 10% above the standard or expected deaths in the subpopulation. Okay, so in the one case, we have a lot fewer people dying, and in the other case, we have a lot more people dying. And in this case, the 20% would be expected because our crude death rate, what was it? I think it was 38.7. Let me just make certain I'm not, 38.7 deaths. You see that right here is less than the expected of the U.S. population, which was, I think, 47.9, if I'm not mistaken, and you can check that value and make certain I'm correct. Okay? Now, people say, well, why do we bother with the SMR indirect? Because it's frequently used in Canada and Europe, because those are places where we do not have specific age-specific, race-specific death rates. All we have is for each age-adjusted group. Okay. All right. Now, I wanted to show you an example here. People ask, well, are these things used and reported? Well, absolutely so. And if you look at this chart, it's from 1980 to 2009, and it's talking about accrued death rate versus age-adjusted death rate. Now, and this is for a diabetic population. If we follow it, and we have the crude values, it looks like there's better progress being made in the treatment or intervention of diabetes in the U.S. And we would draw conclusions based on these values. When you adjust it, when you adjust the values, it shows that we're not making quite the progress that we thought we were making. We might be making good progress. We may not be making very good progress. We'd probably go to Healthy People 2010 and say, what are the objectives for the nation, and are we meeting those or not? Okay, so I think I can summarize it right here with you. The age-adjusted rate decreased 64%. From 48.4 per 100,000 diabetic in 1980 to 17.3 per 100 in the diabetic population in 2009. Well, you can see that that adjustment, if you go back, you can make a statement here that would correspond to the one written here, and you can see that the age-adjusted SMR doesn't show the same results at all as the crude death rate, and the most valid interpretation is the one that we make with the adjusted rate, the adjusted death rate, or using the SMR direct method. Okay? Now I got another graphic to show you, and this is the last one. And this is a selected 1995 age-adjusted death rates. And this is also the use of the the direct method. And you can see that in looking at cardiovascular disease, coronary heart disease, and stroke, that based on the age-adjusted death rates, we should be, this is all races, this is Asian American Pacific Islanders, much lower, right, between this and the total population, and coronary heart disease much lower, and stroke about the same. So what we might conclude from this is that we ought to be looking at the Asian population in terms of what they're doing, since their death rates are so much lower than the total population. What is it then? We would begin to, use analytic epidemiology to ask the question: is what is it then that they're doing that the total population is not, that helps reduce these two diseases, cardiovascular disease and coronary heart disease?